One of the key elements of mathematics at its best is the element of surprise, and I'd like to show you a geometrical result that really surprised me when I first saw it a very long time ago. It concerns a circle, and I've drawn a circle here already, marked its centre O, and drawn a diameter and marked the endpoints A and B. And I've drawn a third point, P, just some point on the circle, and joined P to A and B by straight lines. And when I first saw this result, I remember thinking, okay, I've got some angle here, but that presumably, that angle depends on where the point P is on the circumference. But no, it doesn't. Wherever P is on the circumference, this angle is always the same, and not only that, it's always 90 degrees. And I'd like to give a casual demonstration of that with this piece of card here with a right angle. I'd like to show you how that appears to fit exactly. That angle there is 90 degrees. Or, well, what have we actually shown here? What we've actually shown is that this angle is approximately 90 degrees when P is in the particular position on the circumference I happen to have drawn it. But as I say, it's exactly 90 degrees no matter where P is on the circumference. And why is that really true? How can we prove that? The answer is we can prove it very simply, in fact, by what I think is a lovely piece of geometry, which begins by just joining P to the centre of the circle O by a straight line. The point of doing that is that these lengths here, this one, and this one, are all the same, because they are all radii of the circle. And as soon as we've done this, we realise that we suddenly have two isosceles triangles in this diagram. One is this one, with two equal sides here, and the other is over here with these two equal sides here. And a simple property of isosceles triangles, which you may know, is that if you've got such a triangle with two equal sides, the so-called base angles, these ones here on this diagram, are equal. And that's essentially all I need to use to get this proof going. If I look at this triangle here, this isosceles triangle here, those are the two base angles. And I will label them, say, B. And in this triangle here, these are the base angles. I will label them A. We're almost there, believe it or not. The final part of the proof involves taking the whole triangle, here, the big one, ABP, and using the fact that the angles of any triangle add up to 180 degrees. And if I do that, this angle here is A, that angle is B, and the third angle of the big triangle is A plus B, and so the sum of those three angles must be 180. So two lots of A plus B is 180, and therefore A plus B equals 90 degrees. And that's what I was trying to prove. That proves that that angle there is always 90 degrees, no matter where P is on the circumference. It's true that if we move P around the circumference, both A and B will individually change, but the sum, A plus B, will not. I've just proved that that's always 90 degrees. And to me, this is an example of mathematics at its very best, essentially because one minute you're presented with this theorem and you think, oh, that's extraordinary. I don't believe that for a moment. It goes against my elementary intuition. And what, just 2-3 minutes later, having seen the proof, we think, arguably, oh, it's obvious, really, isn't it? When you look at it the right way, it's kind of obvious, isn't it? And to me, whenever that happens, it's an indication that what you've just seen is an example of mathematics at its very best.